So in this video, we're going to look at 4.5, which is the dimension of a vector space. So we've been talking a lot about what it means to be a basis for a vector space, and we're going to apply that theory and look at the dimension of a vector space. There's a few theorems that I want to go through first, looking at some of the theory behind this, and then we'll go into a definition about the dimension. So first of all, I want to look at the first theorem that's in this section. And it looks at the amount of vectors that you have in a basis and how many vectors you would need in order for them to be linearly dependent. So if we start off with a vector space V, with a basis, as always we'll call it B, and the elements in the basis are going to be the vectors b1 through bn. Then if I take any set of n, of more than n vectors that are in that vector space V, they have to be linearly dependent. Okay, we've talked a bit about this before, but we've talked about it in terms of Rn. But this is actually the case for any vector space V. So if you've got this vector space V that's got this basis b1 through bn, then any set of vectors where you have more than n vectors must be linearly dependent. So if you have n vectors in your basis and then you take any random vectors from V where you take more than n of those vectors, you have to have that those vectors are linearly dependent. Okay. Now we know that this is true in Rn. Okay. If I take, let's say, 4 vectors that are in the real 3 space, I know that those 4 vectors are linearly dependent. We've talked about this before, but we haven't talked about it for other vector spaces. So what I'm going to do to prove this is to tie it back to what we know about Rn. So if you take the vectors, we'll call them u1 through up, where p is strictly greater than n, okay? And each vector is in V. Okay, so I have p vectors, they all land in V. And I know that I have a basis for V that has n vectors in it. So I'm taking more vectors than what I have in my basis. Now what I want to do is I'm actually going to do a change of coordinates to this. So each one of these vectors at the moment is in V. I'm going to do a change of coordinates to make these vectors to have coordinates in terms of the basis B. And what I am doing by doing that, remember, by doing that change of basis, you go from the vector space V to Rn. Okay, so when we do this change of coordinates where we go from some vector in V, by putting it in terms of coordinates in the basis B, you are taking it from V into Rn. Okay, we did this before when we looked at a change of basis. So I've started out with u1 through up are in V, but I'm going to do a change of basis on each of these. Okay, and by doing a change of basis on each of those, each one of those is in Rn. Okay, now I'm in Rn, I'm in the space that I know. I have n-dimensional vectors here, so each one of these vectors has n entries, but I have more than n vectors in Rn. Okay, I have p of these vectors. So I know that these must be linearly dependent. Okay. Now, I didn't know that U1 through UP were linearly dependent in V. That's what I'm trying to prove. But I know that by doing this change of basis and pulling them into Rn, I know that those new vectors that I have in terms of the basis B, those vectors are linearly dependent in Rn. So because they are linearly dependent, going back to our definition of linear dependence, okay, I know as they are linearly dependent that not all of my CI's are going to be 0, okay? If they were linearly independent, I would know that every CI would have to be 0 in this case. But because they are dependent, I have to have at least one CI does not equal 0, okay? So not all of those C's are equal to 0. Carrying on from that, I'll actually come back here for a second. We can expand this, okay? When you take a vector and then you perform a change of basis on it, okay? All you are doing is a linear transformation. You are taking it from one vector space to another. And we looked at this being a linear transformation that was 1-to-1 and onto, if you look back at your notes. This was done in 4.4. So because it's a linear transformation, I know that I can pull each of these scalars into my linear transformation and I can combine them. So if I do that, I would end up with that, okay? So I now have all of my vectors are put together with the scalars because I know that that change of basis is a linear transformation. Now, when we do this, okay, this is just the 0 vector. Okay. When you take a vector and change its basis, so I've taken this vector here, okay, it's all these vectors added together. You've taken a linear combination of vectors, it's just another vector. So I've taken my linear combination of vectors and then I want this in terms of my basis B, okay? And when I do that, remember, the vector that I get is just the coordinates of the vector in terms of that basis, okay? So what I essentially have here is that my original vector, okay, can be written in terms of my new basis B, where these here are my coordinates, okay? So remember, that means that they are the coefficients of each of the basis vectors. So I would get 0b1 plus 0b2, etc., all the way along. Okay? That, of course, is equal to 0. Okay? Now, I know here, okay, from what I've done here, I just get the 0 vector. So I've basically undone what I already had, okay? So I knew that doing this change of basis, it would equal the 0 vector. But what I have now done is I have expanded that. So I know that by doing this vector in terms of the basis B, it can be written as the original vector is equal to this. If you go back to where we did our change of basis, you may have to look back because it's been a couple of weeks since we've done this. But that means that I could just write my original vector in terms of my basis B, which is what I've done. And that just equals the 0 vector. But I know that not all of my CI's are equal to 0. So because I have now taken it back in terms of my vector space V, I know that each of my UI's must be linearly dependent. So as not all CI's are equal to 0, that means U1 through UP are linearly dependent in V. I recommend you go back and look at the first part of chapter 4 where we looked at this change of basis, because it is important in this proof. I'm not going to ask you to replicate it, but you should be able to follow the steps through from what we've done early on in chapter 4. Okay, so we've kind of expanded what we knew for Rn and now applied it to any vector space V. So we already knew in Rn, if I took more than n vectors in n space, that they were linearly dependent. But what I have now said is if I have some vector space where there are n elements, n vectors in its basis, if I take more than n vectors within that vector space, they must be linearly dependent. So I've expanded what I already knew for Rn to any other vector space. Kind of along the same lines as this, I want to carry on to another theorem here. Okay. If you take some basis for V, so if a basis for V has n vectors. So exactly as we had before, we had a vector space V with a basis B1 through Bn. It had n vectors in it. Any other basis that you choose for V, okay, you can pick any other basis you want, but it also has to have n vectors. So you can't have a different basis for V that has a different set of a different number of vectors in that set. So if a basis for V has n vectors, then any basis for V must also have n vectors. Okay. Classic example to think about here is Rn. Okay. We know that, let's take R3 for example. So okay, I know that I can take my standard basis. So I already know that I can take this as my basis for R3. Okay. Now, what I can also do to find a basis for R3 is just take any three vectors that are in 3 space that are linearly independent and span the space. So any set of 3 vectors that are linearly independent and span the whole space. So I can take any linear combination of the vectors that I pick and end up with any vector that I want in R3. They also form a basis. Okay, so I know that there's infinitely many possibilities that I could choose for a basis for R3. And that is the same with any vector space. As long as you have the same amount of vectors that they are linearly independent and they span the whole space, then you have another basis. But you couldn't pick a basis that had a different number of vectors in it, because either you would end up with too many vectors, in which case the vectors wouldn't be linearly independent. So if I had, let's say, 4 vectors in R3, they're not going to be linearly independent. There's going to be at least one that depends on the other. And if I had less than 3 vectors in R3, well, they couldn't span the whole space. For example, if I just take this vector and this vector, okay, so I just take 1, 0, 0 and 0, 1, 0. That is 2 linearly independent vectors in R3, but they can't span the whole space. Okay, I have no z component here. Okay, I've got zeros for my third entry, so they can't span that z component in R3. So I know that they don't span the whole space. So you have to have exactly 3 vectors to span R3, and that is the same with any vector space. Okay, as when you find a basis for it and it has that certain amount of vectors, any basis for that vector space must have that same amount of vectors. Okay, couple of definitions before I talk about the actual dimension. If V, this vector space, is spanned by finitely many vectors, then it is a finite dimensional vector space. Okay, most of the stuff that we deal with will be a finite dimensional vector space, normally real n space, as we've just been talking about. Okay, if it can't be spanned by, let's say, R3 can be spanned by 3 vectors, okay, so it's a finite dimensional vector space. If it cannot be spanned by finitely many vectors, it must be an infinite dimensional vector space. Okay, so in this case, for most of the stuff we deal with, there'll be finite dimensional vector spaces. The other thing that you have to be aware of, just as like a convention, the 0 vector space, which just contains that 0 vector. So all it contains is the 0 vector. That we say has dimension 0. So even though it technically has one vector in it, being the 0 vector, we actually count it as having dimension 0, just as a convention. Okay, so just be aware of that. But most of the stuff we deal with, okay, like you see in Rn, okay, it's spanned by n vectors. So it's a finite dimensional vector space. We tend to call the dimension of the vector space, we tend to denote it as dim v, okay? And all it is, it's the number of vectors that are in the basis. Okay, so as we said, any basis for a vector space has to have the same number of elements to it. It has to have the same number of vectors. So the dimension of a vector space, so dim of V, is the number of vectors in the basis for V. Okay. Classic example we'll deal with, as I said, Rn is n-dimensional. Okay, so the dimension of Rn is n. Okay, so as I said with R3, if we come back here, okay, R3, it had 3 vectors in its basis, so therefore it's 3-dimensional. Another classic example that we have is actually the space of polynomials of degree at most n. Okay, so polynomials in Pn, let's say you took P3 for example, so polynomials in P3 would have degree at most 3. Okay, so if they have degree at most 3, okay, they're going to be of the form P of t is a plus bt plus ct squared plus dt cubed, okay? A, B, C, and D don't all necessarily have to be non-zero because all the polynomials in P3 have degree at most 3. So it also includes linear and quadratic and just real numbers. It just involves scalars as well. So they don't have to all be cubic. Okay, so just be aware of that. So A, B, C, and D, some of them may be 0 or they may all be non-zero. But a basis for this, so basis is 1t, t squared, and t cubed. Okay, if I take any linear combination of those, I can get any one of the polynomials in P3. So even though it's not a vector, it acts as a vector space. It has the same properties as a vector space, so we're going to treat it the same way. So you could take the span of these 4 things can give me a linear combination of, it's a linear combination of these 4 elements, can give me any polynomial in P3. Because of that, a big thing to always remember, there's 4 elements in my basis for P3. Okay, so I've got 4 elements in my basis for P3. So Pn has dimension n plus 1. Okay, a lot of people forget that because they forget about the 1 that's over here, but scalars, just real values, are included in these polynomials. If we have any subspace of a vector space, so for a subspace, we'll call it H of V, the dimension of H must be less than or equal to the dimension of V. Okay? You can't have a subspace of a vector space that has higher dimension than the original vector space. Okay? It would end up being a larger space because it's spanned by more elements there. Okay? You're going to have more elements in your basis. So if we take the span of that, we're going to get more linear combinations of more vectors, so we end up with a larger vector space. So any subspace has dimension at most the dimension of V. Okay. If we come back to R3 here, okay, R3 itself is a subspace of R3. We talked about this. The 2 major subspaces to always remember for vector spaces are the 0 subspace and the whole space itself. They are subspaces of the vector space. So you can have dimension 0 if you just look at the 0 subspace of a vector space, or you could have dimension equal to the whole vector space. So you could have, let's say, the dimension of R3 is 3, but you could take R3 as a subspace of itself, so that also has dimension 3. So just be aware of that. Don't forget the 2 extreme subspaces as well. We then have something called the basis theorem. And what the basis theorem looks at is looking at a p-dimensional vector space. So for a p-dimensional vector space, call it V, where p is at least 1. So I'm not going to include the 0 vector space in this. If I take a linearly independent set of p vectors, so a linearly independent set of p vectors in V must form a basis for V. Okay, so they're automatically going to span the whole space. In the same way, a set of p vectors that span all of V automatically form a basis for V. So if I know I have a p-dimensional vector space and I find p linearly independent vectors within that vector space, I don't have to check whether they span the whole space. They automatically do, and they automatically therefore form a basis. In the same way, if I have p vectors that span the whole vector space, then I don't have to check if they are linearly independent. They automatically do, and they automatically form a basis for V. So if we think about this, the proof is actually in my notes, but it's very similar to what we've already said for a previous proof. So I'm not going to go through it fully, but I will talk through it. If you want to look at the notes, it is in there. If you look at a set of p linearly independent vectors in a p-dimensional vector space. If I have less than p vectors that are linearly independent, I know that they won't span the whole space because I know I need at least p vectors to span the space. So if I have less than p vectors, I know that I can extend that so that they will span the whole space. Okay? In the same way, if I have more than p vectors, okay, I know that they're not going to be linearly independent. Okay, so I can have at most p linearly independent vectors in my vector space. Okay, if I have less than p, I know that they won't span the whole space. If I have more than p, I know I'm going to end up with linear dependence somewhere. So if I have exactly p linearly independent elements, I know that they span the space and I know that they can't be dependent on one another. So we've got a basis. Okay. In the same way, if I look at p vectors that span the space, okay, if I have more than p, okay, they're still going to span my space, but I know that they're not linearly independent from one another. There is no way that they can be linearly independent. If I go for less than p vectors, they're not going to span my space, but they may be linearly independent. The only way that I get that sweet spot is if I have exactly p linearly independent vectors that span the space. Okay, that is the only way that I can satisfy those two properties. So if you look through that proof, that's what it goes through, but it's very similar to what we've already discussed. What I want to look at is how we can find the dimension of the null space and the column space, because this is going to be used a lot in our upcoming chapters. So if I want the dimension of the null space of A. Now remember, when we found the null space of A, we found the solution to A times X is equal to 0. Okay, so the null space of A was all the vectors that I could pre-multiply or left multiply by A and get 0. Okay, so it's all the X's such that this is true. To find the null space of A, all I did was solve this. So I formed an augmented matrix and I went ahead and reduced it down and therefore solved the system. And our solution, when we found X, it was always in terms of our free variables. So it would be a free variable times a vector plus a free variable times a vector, etc. To find the basis, all we did was we took the vectors that were being multiplied by those free variables, and we looked at the fact that they were linearly independent. They were never dependent on one another. They were always linearly independent. So we know that they're linearly independent and they form a basis. They span my null space because I can take any linear combination of them and I'm going to end up back in my null space. So to find the dimension of the null space of A, remember how we found this. It was always our null space elements were a free variable times a vector plus a free variable times a vector, etc. So the number of elements, the number of basis vectors that I have was always equal to the number of free variables that I have in this system. So the dimension of the null space of A is the number of free variables for the system AX is equal to 0. I'm going to do a quick example of this in a second, but I just want to get through some of this theory first. And then for the dimension of the column space of A, okay, remember the column space of A was the span of the columns of A. So it was all linear combinations of the columns of A. So we then looked at, well, we can reduce this thing down by doing row operations on this thing, we could actually find that all of the non-pivot columns could be written in terms of the pivot columns. So any column that contains a pivot actually formed a basis for my column space. So the dimension of the column space is just the number of pivots that you have. It's the number of pivot columns in A. Okay, I'll do a quick example of this so that we can see this. If I let A equal to this matrix, so A is equal to that matrix. Now, I'm going to reduce this thing down just so that we have it. To find the null space of A, you would, to find null space of A, you're going to row reduce that augmented matrix. And that actually comes down to, I'll write it out so you don't have to do it on a calculator. It comes out to this matrix. Okay, so I've reduced it down. Now I know that I have one free variable already without looking at it. I know that I have no pivot in this column. So I already know that x3 is going to be a free variable when I solve ax is equal to 0. So x3 is a free variable because there is no pivot in that column. So I know that all of the other xi's, x1, x2, and x4 could be written in terms of my free variable x3. So x3 is a free variable. Okay, so if you went ahead and actually found the null space of A, it would be something of the form x is equal to x3 times a vector. If you want to go ahead and solve it, go ahead. But because your solution is going to be of this form, this vector here would be the basis vector for the null space of A, and there is only one free variable. So we know that because there is only one free variable in this system, the dimension of the null space of A is just 1. Okay, it's just the number of free variables that I have because that corresponds to the number of vectors that are in my basis for the null space of A. Now, if I look at this, I also know that when I've row reduced A, I can kind of ignore this part here right now. Okay, the fact that I've set it equal to 0. The column space of A is spanned by the pivot columns in A. Okay, we went ahead and did this before when we looked at the column space. So I know that the dimension of my basis for the column space is just the number of pivot columns that I have. So any columns that contain a pivot. So that's 1, 2, and 3. So the dimension of the column space of A is equal to 3. Okay. You will probably notice something has happened here, that we have actually included all of our columns, and that actually comes up later on when we look at some of this stuff and some more stuff to do with rank in 4.3 or 4.6, sorry. So go ahead, try some of the examples that are actually in the textbook under this chapter. It might be good to work some of those problems before I give you homework for this. But if you have any questions, feel free to let me know and I will be happy to help, and I will see you in the next video.